Hello, welcome to the analysis of PFAS in drinking water presentation. My name is Abdurrahim Abdulkawi, and I am an application chemist at United Chemical Technologies. First, I would like to go over general terminology, and then I would like to go into some recent application notes that we have developed on EPA 533 and EPA 537 methods. Per and polyfluorinated substances, known as PFAS, were previously referred to as perfluorochemicals, or PFCs. It is a class of more than 4,000 different chemicals. It is found everywhere. It turns up in everything from household items to fast food wrappers. It has even been found in our blood. PFAS is a group of chemicals used to make fluoropolymer coatings in products that resist heat, oil, stains, grease, and water. These fluoropolymer coatings can be multi-purposed. They can be used in clothing, furniture, adhesives, food packaging, heat-resistant non-stick cooking surfaces, and insulation of electrical wire. The primary sources of PFAS contamination include manufacturing sites that produce PFAS or use PFAS in industrial processes and release the chemicals into the environment through wastewater discharges. These discharges can ultimately lead into surface water or municipal sewer systems that have the potential to leach into groundwater and surface water. In a study published by the Institute of Biogeochemistry and Pollutant Dynamics in Zurich, Switzerland, in October of 2020, categories where PFAS have been employed along with the magnitude of the uses was presented. The study clearly demonstrated that PFAS are used in almost all industry branches and countless consumer products. This includes plastic and rubber production, coatings and paints, manufacturing of metal products, electronic industry, and building and construction, to name a few. Several studies examined possible relationships between levels of per and polyfluoroalkyl substances in blood and long-term health effects. These substances tend to bioaccumulate in humans and may take a long time to be metabolized. High levels of certain PFAS may lead to serious health conditions, some of which are increased cholesterol levels, changes in liver enzymes, small decreases in infant birth weights, decreased vaccine response in children, increased risk of high blood pressure or preeclampsia in pregnant women, and increased risk of kidney or testicular cancer. When we dig into these compounds a bit further from a chemical perspective, it's easy to illustrate how these become classified as forever chemicals. Fluoropolymers are categorized as either non-polymer or polymer. Non-polymers are per and polyfluoroalkyl substances. Perfluoroalkyl substances are compounds for which all hydrogens on all carbons have been replaced by fluorines except carbons associated with functional groups. Polyfluoroalkyl substances are compounds for which all hydrogens on at least one carbon have been replaced by fluorines. Contrastingly, polymers can be composed of a carbon-only backbone, and they can have variable composition of carbon and oxygen or alternative atoms in the backbone structure. To explain this in a bit more detail, let's take a look at short versus long-chain PFAS. PFAS molecules are remarkably diverse in their molecular structure and properties, so much so that we categorize them into two different variable chain length groups. I am presenting a couple examples here from two different EPA methods, 533 and 537.1. PFBA, known as perfluorobutanoic acid, for instance, is a very prevalent PFOS short chain molecule. It is composed of a small carbon chain with a carboxylic acid as a functional group. PFBS, known as perfluorobutane sulfonic acid, is similar to PFBA. However, it has a sulfonic acid instead of a carboxylic acid functional group. As for our long chain examples, 11-chloro-ico-safluoro-3-oxanodecane 1-sulfonic acid possesses a much more extensive carbon chain with an oxygen atom in the middle. Also, N-ethyl-fosa, known as N-ethyl perfluorooctane sulfonamidoacetic acid, is another long-chain PFOS molecule that has sulfur and nitrogen atoms as part of the backbone of the molecule. The log D values in this slide can give you an idea about the polarity of these analytes and how the length of the carbon chain and functionality of the overall compound contribute to that from an extraction perspective. Now that we have a better understanding of the chemical nature and environmental persistence of these emerging PFAS, let's dive into the applicable EPA methods published for monitoring them in drinking water. Let's start with EPA method 533. This method consists of a solid phase extraction technique coupled with a liquid chromatography tandem mass spectrometry LC-MS-MS, which aims for the determination of 25 target PFAS in drinking water. It addresses challenging 4-carbon and 5-carbon acids and solvanates that are in EPA methods 537 and 537.1. It also provides short-chain PFAS analysis by limiting the chain length of the 12-carbon acids. The addition of emerging PFAS via weak anion exchange SPE served as a solution to reliably and accurately monitoring them. EPA method 533 specifically references the use of a weak anion exchange polymeric SPE sorbent. UCT'S ECWAX is just that, a weak anion exchange polymeric column that is very efficient when monitoring the compounds targeted in this method. It is assembled with polyethylene fritz as opposed to PTFE to eliminate any possible cross-contamination. The anion exchange and reverse phase retention mechanism are employed at a sample loading pH of 6 to 7. To showcase this method in a bit more detail, this slide represents the solid phase extraction steps specifically dictated in EPA method 533. It consists of conditioning the column, loading the sample, a wash step, elution, then evaporation and reconstitution. One of the critical steps in this method is keeping the sorbent bed wet. This is a crucial component during the extraction itself to prevent potential breakthrough of analytes. From an analytical perspective, this slide showcases our HPLC conditions for EPA method 533. Using a Nexera Shimatsu UPLC pump, separation is achieved via a Selectra C18 100 mm length, 2.1 mm internal diameter, and a 3 micron particle size. It was particularly important to also install a delay column to track any potential contamination coming from our system. Finally, we also utilize the guard column for good measure just to increase the lifetime of our analytical column. The LC gradient we developed for this method is almost identical to that of the published EPA method 533. We maintained the same slope and tried to shorten the column equilibration time. The column pressure did not exceed 2500 psi. The MS conditions for this method were slightly different than previous conventional methods we ran in our instrumentation. We had to lower the desolvation and interface temperature to prevent the loss of some critical compounds, such as the HPLD. Under high temperature, this analyte showed signs of degradation, and we were not able to ionize it effectively. This slide showcases calibration curves from some featured analytes, PFBA and HPLD from EPA method 533. We obtained excellent linearity with an R-squared value above 0.999. This ensures the accuracy and precision of our results, which I will present in a later slide. For method acceptability, recovery for all compounds must be within 70 to 130%. You can see here that we have obtained excellent recoveries using the EnviroClean ECWAX column. The recoveries were above 95% at low and high fortification levels. The relative standard deviation did not exceed 10%. Both short and long chain analytes were well retained in the column with no observable breakthrough. This is an example of an extracted sample at low fortification level of 10 nanogram per liter in reagent water. We obtained excellent peak shape and baseline separation of all analytes in the method. In addition to that, this slide showcases the baseline separation of some critical compounds in EPA method 533. These two peaks are the perfluorohexane sulfonic acid linear and branched isomers, which are nicely resolved on the UCT'S Selectra C18 HPLC column. Next, we would like to discuss EPA method 537.1. EPA method 537.1 consists of solid phase extraction technique coupled with a liquid chromatography, tandem, mass spectrometry, LC-MS method that aims for the determination of 18 target PFAS in drinking water, including HPLD. The original method was released in 2018 and updated in 2020 to version 2.0. The only updates were editorial in nature and did not include any technical revisions. Since the development of method 537, more PFAS that have the potential to contaminate drinking water have been identified or introduced as PFOA or PFOS alternatives in manufacturing. This updated method can be used to quantitate them accordingly. UCT offers two acceptable chemistries for EPA method 537 and 537.1. Both ECDVB and ECHLD are polystyrene divinylbenzene-based polymeric SPE columns for maximum reverse phase retention for the analytes monitored within these methods. The two major differences between the two is ECDVB is a standard polystyrene divinylbenzene polymer where the ECHLD is a highly retentive cross-linked polystyrene divinylbenzene copolymer. Both columns are manufactured with polyethylene frits to eliminate any possible cross-contamination. To showcase this method in a bit more detail, this slide represents the solid phase extraction steps specifically dictated in EPA Method 537.1. As in EPA Method 533, it is a very straightforward SPE method, where one would condition the column, load the sample, elute, then evaporation and reconstitution. No wash steps are included in this method. Again, one of the critical steps in this method is keeping the sorbent bed wet. We cannot stress enough how critical this is in preventing unwanted breakthrough of analytes of interest. Following the extraction method, the HPLC conditions for EPA Method 537.1 are outlined below using again a Nexera Shimatsu UPLC pump and UCT'S Selectress C18 50 mm length, 2.1 mm internal diameter, and a 3 micron particle size. Since we are monitoring less analytes than EPA Method 533, we have selected this 5 cm column instead of the 10 cm used previously. They are both very comparable. The one advantage we had was at the overall system back pressure, which was lower than 1500 psi at max. In regards to our gradient of choice, our goal in this setup was to develop a short and robust analytical method. In the official EPA Method 537.1, the runtime approximately 37 minutes per each injection. Our optimized method was only 11 minutes per injection, including the column equilibration time. This is an important distinction to make for labs who are processing a lot of samples and do not necessarily have the time for a 37-minute per sample analysis time. As mentioned previously for EPA Method 533, the MS conditions for this method were slightly different than previous conventional methods we ran on our instrument. We had to lower the desolvation and interface temperature to prevent the loss of some critical compounds, such as HFPODA. Under high temperatures, this analyte runs the risk of degradation and loss of ionizability. To demonstrate our method's linearity, we isolated PFBS and 11-chloroicosafluoro, 3-oxanodecane 1-sulfonic acid from EPA Method 537.1. R-squared values are above 0.999, ensuring the accuracy and precision of our results. For ECHLD, we extracted samples at both low and high fortification levels. The recoveries for all analytes were within EPA's acceptable range of 70 to 130%. Most of the analytes were above 85%. We did notice, as in the case of HFPODA and NET-FOSA, the recoveries were a little bit below that, in the 75% range. As mentioned previously, however, this is acceptable according to EPA's method requirements. For ECDVB, we extracted samples at a single fortification level. In this case, the recoveries for all analytes were above 85% without exception. The column's performance proved to be slightly superior to that of the ECHLD. However, either column can be employed for EPA Method 537.1 since they both satisfy the EPA's chemistry specification. This is an example of an extracted sample fortified at low fortification level 5 nanogram per liter in reagent water. We have obtained excellent peak shape and very nice baseline separation for all analytes in the method, which includes surrogates and internal standards. Additionally, this slide showcases the baseline separation of all surrogates and internal standards included in EPA method 537.1. An important area of focus anytime you are analyzing PFAS is ensuring low background levels within your system itself. This slide showcases just that. This is a necessary step to track any possible contamination that may be arising from the instrument itself to preserve the integrity of your samples. Performing a series of blank injections can ensure the suitability of the system to live sample injections. If high background levels exist, a series of actions needs to be taken, which may include flushing down the entire system and making sure no PTFE components are leaching inadvertently. It is highly recommended to install PFBA-free systems if possible on instrumentation being used for analysis. Not only must you ensure that your instrumentation is free of secondary PFAS exposure, you must also take into consideration your sample extraction and processing equipment. PFBA is known to be a prevalent contaminant when monitoring PFAS in any matrix. Sources of contamination can arise from various points of the extraction, which may include the ammonium hydroxide solvent bottle and lid, the consumable itself, and most importantly, lab processing equipment. This is a typical setup for EPA method 533 or 537.1. There are multiple components that are critical to ensure a contamination-free extraction. These include the stopcocks, the PE lower tips, and the sample transfer lines. UCT has taken several measures to mitigate this background exposure to include a designated glass block manifold for PFAS processing, available for sampling or purchase today. UCT's complete PFAS glass block processing station and accessories provide all facets needed for an efficient extraction. All components are hand-selected to minimize potential for any secondary background contamination. The complete set of the PFAS-free glass block manifold consists of glass block Corian manifold lid, cover gasket, vacuum gauge and assembly, PE clean-through tip, PE stopcocks, adjustable collection rack, bulkhead lower fittings, plugs, glass block safety tray. The glass block manifold system is available in either 16 or 24 positions. Outside of processing water samples, PFAS detection in food and agricultural commodities has become a big focus for not only the FDA, who pioneered the method, but also additional testing labs. Since 2012, the FDA has been refining the analytical method to test specific food groups for PFAS, as well as focusing assessment efforts on foods grown or produced in areas associated with environmental PFAS contamination. In 2019, the FDA expanded the methods used in earlier testing and made available the first single lab validated scientific method for testing 16 different types of PFAS in a highly diverse sample of foods, as in fruits and vegetables, bread, milk, cheese, other dairy, and meat, utilizing a UCT catcher's approach. This method is being used to continue testing foods from the general food supply and in the FDA's work supporting states in assessing the safety of human and animal food from specific areas potentially affected by environmental contamination. This is the list of analytes that were included in the FDA-developed method for PFAS monitoring. We can notice the diversity of the analytes, short chain and long chain compounds, Some analytes are in the EPA method 533 and others are featured in EPA method 537.1. UCT's catcher's blend were able to recover all analytes regardless of their structure or complexity. In the event additional PFOS are being analyzed beyond the scope of this list, UCT does have the ability to further customize the extraction blends to provide optimal cleanup and recovery for the compounds at hand. Finally, UCT has made available a solutions guide for PFOS testing across markets. It features additional information about UCT's SPE, HPLC, and catcher's product for targeting PFOS in multiple matrices. Please visit our website for additional information. Thank you.